Good morning, everyone. My name is Phan Tuan from the Industrial University of Ho Chi Minh City. Today I will present a survey on quantum light and its applications. In this talk, I will briefly introduce what quantum light is, how it can be generated, and how it is used in modern quantum technologies such as communication, computing, sensing, and imaging. I will also mention some key challenges and possible future directions in this field.
Presentation contents including the first introduction to quantum light, the second theoretical foundations of quantum light, the third production techniques for quantum light, the fourth applications of quantum light, the fifth challenges and future directions. Quantum technologies are becoming an important part of next-generation information and communication systems. Quantum light, which treats light at the single photon and few photon level, provides non-classical resources that classical optics cannot offer. In this presentation, I will first review the basic concepts of quantum light, then describe typical generation techniques, followed by representative applications. Finally, I will discuss some current challenges and future research directions related to quantum light. In classical optics, we usually describe light as an electromagnetic wave, or sometimes as a stream of particles. In quantum optics, we go one step deeper and describe light in terms of photons, the quantum particles of light. At this level, light shows genuinely quantum features such as superposition, where a photon can be in several states at the same time, and entanglement, where two photons exhibit strong correlations even when they are far apart. These non-classical properties are the foundation for many new technologies that cannot be realized with classical light alone.
Photons are the basic energy packets of light, and they clearly show wave-particle duality. In some experiments we observe interference patterns, which reflect their wave-like nature, while in others we detect individual photons as discrete clicks in a detector. Their energy is quantized and given by Planck's relation E=h. In addition, quantum light sources can exhibit non-classical photon statistics, such as anti-bunching, which cannot be explained by classical electromagnetic theory. These characteristics make photons very attractive for tasks like secure communication and high-precision measurements. Quantum light can appear in different quantum states, each useful for different applications. Single photon states are essential for quantum cryptography because they allow us to encode and transmit information in individual photons. Squeezed states reduce the uncertainty in one-field quadrature, for example the phase, which directly improves the precision of interferometric measurements. Entangled states contain strong correlations between two or more photons and are fundamental resources for quantum teleportation, entanglement-based QKD, and photonic quantum computing. One of the most widely used methods to generate quantum light is spontaneous parametric downconversion, or SPDC. In this process, a strong pump laser sends high-energy photons into a nonlinear crystal. With a small probability, one pump photon is converted into two lower-energy photons, called the signal and idler. These photons can be strongly correlated or even entangled in polarization, time, or momentum. Because SPDC is relatively mature and flexible, it has become a standard source of entangled photon pairs in many quantum optics experiments. Besides SPDC, there are other important platforms for generating quantum light. Quantum dots are semiconductor nanostructures that behave like artificial atoms. When properly excited, they can emit single photons on demand, with high purity and brightness, and can be integrated on photonic chips. Atomic ensembles use a large number of atoms interacting coherently with light fields. They allow us to store and retrieve quantum states of light, effectively acting as quantum memories. Such memories are crucial building blocks for quantum repeaters and long-distance quantum communication networks.
Applications of quantum light including quantum communication, quantum computing, quantum cryptography, quantum sensing and metrology, advanced imaging techniques.
Quantum light plays a central role in quantum communication and quantum cryptography. In quantum key distribution, or QKD, cryptographic keys are encoded into single photons or entangled photon pairs. Due to the laws of quantum mechanics, any eavesdropping attempt will unavoidably disturb the quantum states and can be detected by the legitimate users. This means that the security comes from fundamental physics, not from the assumed difficulty of mathematical problems, as in classical cryptography. As a result, quantum communication is considered a strong candidate for future ultra-secure networks. Photons can also be used as qubits, the basic units of quantum information. Information can be encoded in various degrees of freedom, such as polarization, optical path, time bins, or frequency modes. Photonic qubits offer important advantages. They suffer very little decoherence, and they are naturally compatible with existing fiber optic infrastructure. By combining superposition, interference, and entanglement, optical quantum computing schemes aim to perform certain computational tasks more efficiently than classical computers. Although large-scale photonic quantum computers are still under development, many proof-of-concept experiments already demonstrate their potential. Quantum light is not only useful for communication and computing, but also for sensing and metrology. Using squeezed states, we can reduce quantum noise in interferometers and measure very small changes in phase or distance. A famous example is the LIGO Gravitational Wave Observatory, where squeezed light has been used to improve detection sensitivity beyond the classical shot noise limit. Similar ideas can be applied to high-precision clocks, gravimeters, magnetometers, and other sensing devices, enabling measurements that go beyond classical limits. Quantum correlations between photons also enable new imaging techniques. In ghost imaging, for example, one photon interacts with the object while its partner is detected by a spatially resolving detector. Surprisingly, the image can be reconstructed from the correlations, even though the imaging detector never directly views the object. Other methods, such as quantum holography, can improve contrast and resolution, especially under low light or noisy conditions. These techniques are promising for applications in biomedical imaging and microscopy, where high sensitivity and low photon flux are often required. Despite its great potential, the field of quantum light still faces several significant challenges. First, we need better sources with higher brightness, purity, and indistinguishability, as well as lower loss in optical components and channels. Second, it is crucial to achieve scalable integration of quantum light sources, detectors, and circuits into large-scale quantum photonic integrated circuits. Third, building real-world systems requires substantial investment, interdisciplinary collaboration, and improved public understanding of quantum technologies. Looking ahead, exciting directions include hybrid quantum systems, global quantum networks using satellites and fibers, and using quantum light to explore fundamental questions in physics.
My presentation ends here. Thank you for your attentions and watching. See you later.